Hi guys, so this video is going to walk through the theory behind our lab on the stoichiometry of a hydrated compound. So first of all, what is a hydrated compound? Well, a hydrate is a crystallized salt that has loosely bound water molecules. So again, a salt here is going to have some water molecules that are associated with it. So the question is, how many water molecules are associated in this salt per formula unit? So as an example, imagine you have the salt sodium acetate trihydrate. So this brings in our understanding of the importance of knowing how to name compounds, because we should be able to take this name and create this chemical formula using the sodium acetate as the salt, and then we represent the number of bound water molecules by using a dot and then the number. Remember, we're going to use Greek prefixes again to indicate the number of water molecules that are in the name. So specifically, sodium acetate trihydrate would have 3 water molecules that are associated per formula unit. So what are we doing in this lab? Well, we're just using a different salt. We're going to be using copper 2 sulfate, and we're interested in finding out how many water molecules are associated for each formula unit of copper sulfate. Okay, so how are we going to do this? At the end of the day, we're really just going to be using heat. We're going to have a mass of our copper sulfate that we weigh. We're going to be heating it to drive off all the water, and then we're going to weigh it again, and that difference will tell us how much water came off. And then there's some calculations using molecular weights and stoichiometry to allow us to figure out how many water molecules are there. So here's the details of what we're going to do experimentally. I want to make sure to highlight that Dr. Brown has a great video that goes through a lot of the experimental work, but we're doing things a little bit differently this year. We're going to be using a Bunsen burner to actually provide the heat rather than a heat plate. Okay, so there's 2 videos there that kind of show Bunsen burner use, and then the overview of the experimental work uses a heat plate. So we're going to be using a Bunsen burner. And also, because we're using a Bunsen burner, we're going to heat our salt in a test tube. We're not going to heat it in a beaker. So just make sure you keep that in mind as you watch those 2 videos to understand that we are doing things experimentally a little bit differently. Okay, so here's how this is going to work. The first thing you're going to do is you're going to mass on an analytical balance. Remember, analytical balances will give us to 4 significant figures. So make sure that you have that data in your data table. You're going to mass an empty test tube, and you'll record that in your data section. After that, we're going to take about 2 to 3 grams of copper sulfate. Now, there's a couple of ways that you can do this. One way is you can just take a piece of weigh paper and put about 2 to 3 grams in there. And then once you know you have around that range, you don't need to write that number down. You're going to transfer that into your test tube. So that's one way to do it. Another way is you can actually just with your scoop put it directly into the test tube. But at the end of the day, we want to then mass our test tube plus our salt. And looking at the difference of those 2 values, we will know how much salt is in that test tube. Now, why it's important to not just mass it on the filter or on the weigh paper and then just transfer it in is there's still going to be some of that salt that's left on the paper. We won't have what we call quantitative transfer. So this is an experimental method that will allow us to make sure that we have all of that copper sulfate hydrate accounted for. All right, so the next part is where we're using a Bunsen burner again instead of the heat plate. So a great video that Dr. Brown has on Bunsen burner safety. Importantly, we do need to make sure we follow good safety protocols when using a Bunsen burner. Not only is it a flammable gas, but because there's a flame, we need to make sure that any loose items of clothing or hair are properly secured so that we don't have any accidents. But what you're going to do here is you're going to use your test tube holder, and you're going to hold onto your test tube, and you're going to gently heat it in the flame. So again, gently heating it means constantly moving it around. Think of making popcorn, right? You don't just kind of put popcorn in a pan and let it sit on the stove. You're constantly sort of shaking it so that all of it gets heated evenly. We want to be thinking about the same principles here with our chemical experiment. So you're going to heat this for about 10 to 15 minutes, making sure to note, be careful not to scorch or burn your salt. We just want to be using some gentle heat to drive off all of the water molecules. When you think you've kind of gotten all of it off, and I probably could have changed the color here, you start with a salt that's light blue in color. When you've actually gotten rid of all of the water, it's going to be like a pale gray or a white salt. So that's an indication that you're probably ready to take your first weight measurement. So set it aside to cool for just a little bit in a beaker. The main reason is you don't want to be touching that hot test tube. Now, again, you're not going to be touching anything with your hands here. I know this is something Dr. Brown mentioned in the video. Even the oils from your hand can be transferred to your test tube, and that can be a problem because that's going to add weight. Keep that in mind. Remember, I'm always going to be asking you to think about why your stuff is high or low. Hopefully that's not going to be a reason why, because you won't be touching it with your hands. But those are the kinds of things I want you to think about as to why your measurements might be high or low when you have your final result. So we're going to mass now this test tube and the salt, and we're going to take and write down that number. You're going to go through one more heating cooling cycle, and you're going to get another mass. The reason that we're doing this is we ultimately want to look at the difference. If there's no change between the end of your first heating and the end of the second heating, then you're done. You know that you've driven off all the water. Remember, if we're still seeing a weight decrease, that meant there was still water that needed to come off. So you may even need to do this a third time. If you said that between C and D there was additional water that came off, you need to make sure that you stop only after you have 2 measurements that do not show an appreciable change in weight. And that's going to be no change more than 0.05 grams. Okay, so once that happens, we know that we're done. All the water is gone. And what we have is not a hydrate. We have a salt that we call anhydrous, or without water. So we're going to have copper sulfate that has no water in. Okay, so what are we going to do with all of these numbers? Remember, there should be 4 data points that you have in terms of masses you've measured to 4 significant digits. We started out with the mass of the test tube, and then we had the mass of the test tube plus our hydrated salt. And then we took our first mass after we heated it, but we didn't know if it was fully anhydrous, so we heated it again. And once we saw that there was no change more than 0.05 grams, then we know that we truly do have an anhydrous salt. So taking the difference between B and A, that will tell us the mass of the copper sulfate that we had. And if we take D minus A, notice that C is not what we're going to use for our calculations. It's just making sure that we know we have all of the water driven off. But now this anhydrous salt minus the mass of the test tube, that will give us the mass of the anhydrous copper sulfate. Now, looking at the difference between these 2 values will tell us the mass of the water that was lost. Okay, sometimes pictures are easy to understand with this than words. So we started out with this blue crystal that had some water with it. We're going to try to figure out how much water is with it. So after we've heated it, and we've heated it to make sure that we've driven off all the water, we have an anhydrous solution, or salt of copper sulfate. Remember, this is not going to be blue in color. That's our indication that we've driven that water off. And so all of the water will have been lost. So this total mass will allow us to then figure out the difference that is the water that was driven off. I'm not going to spend too much time talking about these calculations. There's going to be a lot of heating and waiting time that we'll have in lab that will actually go through the calculations so you can finish this lab before you leave. But just as a little preview, right, here is the mass of the copper sulfate that is hydrated. Right? This is how we get the mass of the copper sulfate that's anhydrous. And really, we're looking at the difference in these because we'd like to know the mass of water that was lost. So what are you going to do with these numbers then? Well, we need to convert things into moles, because remember, moles is what we're interested in. Stoichiometry uses moles. When we're talking about molar ratio of things within a compound, it's a ratio of the number of moles. So if we want to figure out what this X value is, that's the molar ratio of the number of moles of water in a compound compared to the salt. Okay, so we can use molecular weights here for copper sulfate and for water to ultimately get to the number of moles that we knew was in that water or that hydrated salt, and then the number of moles of the copper sulfate that was there. And that molar ratio will allow us to figure out what that X value is. All right, good luck.